All right, welcome back. Happy Wednesday. Today we're going to talk about something called Taylor polynomials. You're working on project number 8. I'm working on grading quiz number 5. It's going to be a while before I finish grading quiz number 5. You had to write 5 proofs, and so I have to read 5 proofs times like 32 students. It's 160 proofs. It's going to take some time. I'm working on it. Coming up not too far away, May 5th, is our third and final test. Any questions on the calendar? We have a final exam. Good try though. All right, let's jump in again on page, I think we said, let me see, 40. So we're actually going to jump to 48. We're going to skip 47. We're going to jump in. I'm going to tackle part of your activity today. Okay, so here's the setup. We're considering the function f of x equals e to the 2x. And the graph of that function looks an awful lot like the graph of e to the x, which we know is just an exponential decay, exponential growth. So there we go. And what we are going to do is try to approximate that function with a polynomial. Approximate this thing here with a polynomial. And the reason we want to do that is that polynomials are some of the nicest, simplest things to work with in any number of contexts, like taking derivatives and taking antiderivatives for polynomials, really easy. Now, you can say, hey, the antiderivative of e to the 2x is also easy, and I agree. But for example, if it was the integral of e to the 2x times sine of x, I don't know if you remember, we did something almost identical to that, and it was like a lot of work. It was 2 integration by parts, a ton of algebra, and if I just change it to like e to the x squared, all of a sudden it's impossible, right? So like it's really easy to make integrals with e's in them that are hard to impossible. But if that e to the x squared was some polynomial, maybe x cubed minus 5x, it's a whole lot more manageable now. So this is the ultimate goal of this section. And so, here's the approach. What we're going to do is we're going to pick a point that we want to focus our attention on. In this particular case, the x value that we're interested in is going to be 0. So we're going to focus our attention right here. You can pick any point. It's going to be given to you in the problem. For this one, it's just sort of arbitrarily chosen to be x equals 0. And what we're going to do is try to find a polynomial that hugs the e to the 2x curve near that green point. And the polynomial we're going to start with here is a degree 2 polynomial. Now you guys know the kind of generic degree 2 polynomial. Degree 2 meaning x squared, right? So ax squared plus bx plus c is a generic degree 2 polynomial. We're going to call this guy p sub 2 to match the degree, because you're going to do a third degree in the activity. And it's totally fine to write it as ax squared plus bx plus c, but it's going to be more generalizable if instead of a, b, and c, we call it a sub 2, a sub 1, and a sub 0. So it's just constants to be determined, but it just turns out it's going to be easier to go farther with this if we use these subscript things instead of the a, b, and c, okay? So we're focusing our attention on this guy right here, and we are going to try to find the values of a0, a1, and a2 to make that quadratic match or hug this e to the 2x as closely as possible near e to the near x equals 0. So I'm just going to draw like a quick parabola. Maybe it's something like this. It's okay, you know, they're decently close to each other at x equals, or at that green point right there. We're going to pick the a0, a1, and a2 to make them as close as possible to each other at that green point. Levi? No, it's just a convenient way to enumerate them. Yeah. Okay, so here's the strategy. We are going to calculate, so again, f of x is e to the 2x. That's the function we're trying to approximate. We're going to find f of 0, f prime of 0, and f double prime of 0. Separately, we're going to find p2 of 0. That's the generic parabola thing here. We're going to find p2 prime of 0 and p2 double prime of 0. And once we've got those 6 numbers, These ones are going to have A's and B, or A0s and A1s and A2s in them. We're going to match them up. We're going to make f of 0 equal P2 of 0. And we're going to make f prime equal to P prime. We're going to make f double prime equal to P double prime. And we're going to solve equations that will tell us what A0, A1, and A2 are. Okay, we're going to pick those numbers to make it so that these two functions have the same y value, the same first derivative, and the same second derivative. That's the process. Okay, so let's follow the process. All right, so I'm going to recopy f of x right here. That's e to the 2x. And then I'm going to calculate f of 0. What is it? That's 1, right? E to the 2 times 0. That's 1. And then we're going to do f prime of x. So what's the derivative of e to the 2x? Say again? Nope, it's not that. Yeah, yeah, so it's e to the 2x times derivative of the stuff, right? Chain rule says times the 2, okay? And coming over here, what is f prime of 0? Plugging 0 in for x. It's 2, right? 1 times 2. Okay, and then one more. F double prime of x equals. So we're taking another derivative here. What do we get? Isn't it 4, right? E to the 2x times another 2 times another 2. And f prime of 0 is therefore 4, right? 1 times 4. Okay. So nothing mysterious there. All we did was take the given function, the e to the 2x function, and we found its y value at 0, and we found its slope at 0, and we found its concavity at 0. 3 numbers. Now we're going to start over and do exactly those calculations, but on my generic quadratic up here. So we're going to rewrite the original and then find its derivative and its second derivative. So here we go. So I'm just going to copy P2 of x, circled in red. And then we're going to calculate P2 of 0, plug 0 for all the x's. What do you get? A sub 0. Okay, that's kind of nice. And then we're going to do P2 prime. We'll take a derivative of P2. Okay, what's the derivative of A0? Nothing, that's a constant. What's the derivative of A1x? A1 plus, what's the derivative of A2x squared? 2A2x, yes? P2 of 0, 0 for x, what do you get? Just A1, right? That second term just vanishes. Okay, that was so much fun. We'll do it one more time. Looking for P2 double prime now. Yeah, derivative of A1, that's nothing. And then 2A2x just becomes 2A2. We're now plugging 0 into that. Some students get a little bit tripped up here. We're plugging 0 for every x that you see. What do you get? You get 2A2. You do not get 0. You get 2A2, right? That function is now just a constant. It's like something like f of x equals 5. How much is f of 0? 5. And f of 1 is 5. And f of every number is 5. It's not 0. Okay, another opportunity for confusion. A0 is the first answer. A1 is the second answer. Some students leap and say, oh, A2, but it's not, right? The pattern has changed, or at least the pattern we thought was there is not the pattern that's there. Okay, so now what we are going to do is make that parabola and that exponential function agree with each other at these three moments. So I am going to make f of 0 equal p2 of 0. And that's an equation, right? a0 equals 1. That's my equation. And then separately, we're going to make f prime of 0 equal, I missed something here, p2 prime of 0. And then finally, we're going to make, what's happening here? I'm like shortchanging you guys on my primes. Totally missed them here. And we're going to make f double prime of 0 match p2 double prime of 0. Right? Three equations, three unknowns. I'm trying to find a0, a1, and a2. We're about to find them. Okay, I don't think I can keep all these things on the screen, but you guys have them on your page, so help me out. What's the first equation? a0 equals 1. Second equation? a1 equals 2. Third equation? 2 equals 4. It's not supposed to be hard to write those equations, but you got to make sure you see where they come from. If it's mysterious at all, speak up. We're just making those things match each other. Just have to match the right ones. Any questions on those three equations? Okay, so the goal is to find a0, a1, and a2. The first two equations are conveniently already solved. We don't have to do anything, and it's trivial to find a2. So we find it. a2 is 2. And so that means we can now rewrite p2 of x. Remember, it was the thing all the way at the top. a0 plus a1x plus a2x squared. What does that become? The first thing becomes what number? 1. Plus, then it was supposed to be a1x, 2x, plus, then it was a2x squared. What is that? 2x squared. That's it. Okay, and we'll show you a quick graph just so that we see what we have accomplished here. I'm going to graph the original function, which was e to the 2x. There it is. And then we're going to graph this new function, which we just calculated, 1 plus 2x plus 2x squared. Okay, what are we doing here? Labeling, where's the font size? There it is. Okay, so what do we think? Maybe if we make one of these guys a little bit like a different color. Okay, so the blue one is the e to the x, and the black one is the parabola. Do they have the same y value at the x equals 0? Yep. And they also have the same first derivative, although that's not pictured, but they sure look like they have the same slope. And I have a real hard time like identifying or estimating concavity as a number, but we made it so that the parabola and the e to the x, e to the 2x have the same concavity at x equals 0. And you can see that that they are really hugging each other quite well, right? Quite nicely inside of here. Now, the fact is, what do you think? How long are these two functions exactly the same as each other? Like, clearly they're different at negative 0.4, but do you think they're the same at negative 0.2 here? See a couple of different votes here. I see some yeses and some nos. Like, it sure looks like they're the same. And if they're not the same there, then maybe at negative 0.1, they're the same. What do we think? For how wide of an interval are these two functions exactly the same? Maybe negative 0.1 to 0.1? All right, well, let's keep peeling here. All right, so there's negative 0.1 and there's positive 0.1. I really can't tell these two functions apart. Let's stretch vertically here. What do you think? Same or different at negative 0.1? What's happening? See the space right here? See how they look like they're the same at that spot? Right, so right around here is where they're the same. So what's happening is I peel up. You see that they are pulling apart here? All right, so I'll ask you again, where do you think they're the same? Only at that one point. It's the only place they're the same. They're really close for a while, and how long they're really close depends on how you define really close. But all we did was make sure that they were the same at one spot. They're not the same anywhere else. Okay, so I think that we are golden. Let us continue this activity. With apologies, this thing is supposed to be on the next page. It just it's one line too early. So maybe you can go to the next page and copy this thing at the top. That's where it should be. So go to page 49 and just write down this thing here. And then proceed on page 49 with all the questions that are written there.